custom resource definition. For our speaker, let's give a round of applause for Mr. Nish Gullit.
Hello. Okay. Good morning, guys. My name is Nilesh, and I'll be talking about auto-scaling containers with KEDA. So I think Sebastian did a great job in setting the stage with what is Kubernetes. I'll be sort of extending the concept that he explained and show something which is quite interesting, and hopefully you like it. Before I start, I assume that you have basic knowledge of what is Docker, what is Kubernetes. Since Sebastian covered part of it, I'm in a safe area. I can at least assume that if you paid attention to what he said, you know at least 10-15% of that now. Little bit of microservices and a knowledge of other Kubernetes service would also help. Can I also do a quick show of hands to know how many are from developer background or developers? Everybody or very good? Okay. How many are administrators or operations? Okay. In terms of programming languages, how many are from .NET side or Java? Go? Anybody? Okay. The reason I'm asking these questions is with Docker and Kubernetes, once you know Docker, it becomes quite easy. The language doesn't matter. The concept of Docker and Kubernetes, they are kind of portable from one language to another. Docker is very few set of commands, like once you know 15-20 commands. Whether you are a .NET developer or Java developer, you can create containers with similar set of commands. So let's start with a big thanks to our sponsors, and I'll start my talk. So who am I? My name is Nilesh Gullit. I'm one of the Microsoft MVPs, and here are some of my details where you can find like my website, GitHub, Twitter URL, LinkedIn. So in case you want to connect with me, feel free. Just mention that you are part of this event so that I know that why you are trying to connect with me. So what's on the agenda? We'll start with understanding what are the different options for scaling in Kubernetes, which is also known as KEDA. I'll talk a bit about KEDA architecture, and we'll also see a live demo of KEDA. So what are the different options for scaling? I think Sebastian covered some of these, so I will not go into minute details of them because you already saw a demo of this. The first one is manual scaling. Manual scaling, you saw Sebastian do like scale, give the numbers, and you increase the number of pods. The next one is load-based scaling. In load-based scaling, we have two different types. One is like cluster auto scaling, where you scale the whole cluster. There is also an option called horizontal pod auto scaling, where you scale only a certain pod, not the whole cluster. So let's say you have a cluster of 3 nodes. In your Kubernetes cluster, there are 3 nodes, and it is not able to create new pods. So you can define rules to say, I want to scale the whole cluster. I want to dynamically add more nodes. If you have the space, then you can use horizontal pod auto scaler. And then there is also the concept of virtual node. So we look at all this, and then finally we will look at event-driven scaling. So manual, Sebastian showed this part where the replicas are created. So in this case, let's say the first one, where we are scaling just a Kubernetes object. So here, if you look at the first option, so this case where we are scaling KEDA objects. So we're trying to scale replicas to 3, and it's a processor deployment. It's a deployment where we are saying it's a type of Kubernetes object named processor deployment, and I'm creating 3 replicas here. I can also give like a YAML file. So the first one is YAML file. Whatever is defined in that YAML file, those objects would be scaled to 3 replicas. The second one is where it is already deployed into the cluster and it's named as deployment RabbitMQ consumer, for example. This would scale to 3 replicas. The bottom part is where I'm scaling the whole cluster. So I'm saying scale this, node count is 1. I can also specify what should be the maximum size or maximum number of nodes and what should be the minimum number of nodes when I scale. So I can give like minimum 4, maximum 10. So when it tries to automatically scale the whole cluster, it will not go beyond 10 nodes. So what's the benefit of manual scaling? The first one is obviously the operator who is doing manual scaling. He is completely in charge of scaling it. He knows what he is scaling. Cons is you cannot scale all the objects. Like there are some default objects in Kubernetes like daemon set. Daemon set is like a cron or a daemon job running on each and every node. This cannot be scaled. So this is a limitation of manual scaling. So let's move on to the horizontal pod auto scaling, or what is also known as HDA. So you can see the command there, kubectl auto scale. I have a PHP deployment here, Apache, and I'm giving the CPU percentage as 50%. So in this case, it will automatically scale if the percentage of CPU goes is equal to 50, minimum 1, maximum 10. And the way it works is you can define at what level you want to do the scaling. Pods can be done via deployment, replica sets, or other objects could also create the pods, and this applies only to the pods. So this will not scale the nodes. You are specifically saying any pod which has this auto scaling tool will use this horizontal pod scaling. So the pros of this is it automatically scales the objects based on CPU utilization is quite common. That's one of the metrics which can be specified. You can also specify custom metrics here. So these custom metrics are the metrics which Kubernetes server or Kubernetes API itself has on its own. The cons of this is, again, some objects, daemon set, you cannot scale using this approach. This is also limited by the number of resources on the cluster. So because you are trying to scale individual pods, let's say your cluster has got 4 nodes, and all the resources that are allocated on those 4 nodes are completely full. And you are now at a level, let's say the first example itself, where I'm saying maximum 10 replicas has to be created, and already 8 are created, but there is no space to create additional 2 replicas of that particular PHP Apache deployment. So it will not be able to scale because there is no space on those nodes to allocate these nodes, these pods. So that's a limitation because it's limited by the number of available resources across the cluster. There is one service which is in preview, specifically with Azure Kubernetes service. This is called as the cluster autoscaling. So this is the extension of the previous case which I was saying. So in this case, based on the workload, we are not just scaling the pods, but we are also scaling out the cluster itself. And you can see in the yellow part at the bottom, I'm enabling the cluster autoscaler and I'm defining my min and max counts. So this addresses the problem of limited resources. So you can handle additional compute resources via the cluster autoscaling. And you can also do enabling and disabling of the cluster without having to restart the cluster. So let's say you are experiencing a great workload on your cluster. You enable scaling, you reach a stable state, and then you want to disable it. You don't want to continue scaling endlessly. So using the AZAKS command, you can say from this point onwards, disable the cluster autoscaling. And you don't have to restart the cluster, or you don't have to do any disruptions to your running services. The cons of this approach is it does not support HTTP application routing, and it could increase the cost. So one of the limitations of this auto-scaling is when it tries to scale down, if there are some objects which are created outside of the normal Kubernetes API. So let's say somebody directly creates a pod and this is not known to the Kubernetes API like the replica said, or if there are constraints put saying I want to schedule my pod with, let's say, a node which has a GPU instead of CPU. So those kind of things, because they have a sort of affinity, they cannot be scaled down. And you might have a cluster which is having too many resources, but it's not able to scale down when there is not enough workload on that. The next option is virtual node. So the way virtual node works is this is specifically for serverless scenarios. So in Azure, you have what is known as the container instances, ACI, Azure Container Instances. This can run without having a Kubernetes cluster. You don't have to manage the cluster yourself. You can say, take my definition of a pod, and you decide where it has to be scheduled. So in this case, what happens is, you are just extending your main cluster. So I have this part, which is my main Kubernetes cluster, and let's say in this case, I have 4 VMs, which are part of my initial cluster, and then I want to have a burstable workload, but I don't know exactly how many VMs I would require. So I can say part of this I want to run on Azure Container Instances, and this has to be managed by what is called as a virtual node. So I just get, instead of in the first case where I know there are 4 nodes, I would have just one node as an API or as an interaction point. I won't know behind this how many actual instances are created by ACI. I just have one single pane which talks about 4 plus a virtual node. So this can have n number of pods behind the scenes. And this is giving you a single pane of glass where you can manage them via the same Kubernetes commands. And behind the scenes, this also runs something called as Virtual Kubelet, which is like an open source project. Virtual Kubelet is supported by multiple cloud vendors, not just Azure. You also have support for AWS and various other cloud providers. They support the Virtual Kubelet. So the best benefit of this is it scales very quickly because you don't have to create the VMs. So if you're used on, say, AWS, those instances which are readily available, and you want to use them for a short period of time. So this is a similar scenario where somebody already has the resources, you just say schedule my workload on them without having to manage it. It also provides a higher level abstraction via a single virtual node API. So as I said, there might be multiple VMs running behind, but I don't have to care about them. I can use only one API to interact with my main cluster as well as the virtual node. The cons of this is when it comes to Azure Kubernetes Service, for example, this is heavily dependent on some of the ACI feature sets. And some features which are not supported are like the service principles. So you have, let's say, an image which you want to put into your own container registry. And you want to use a service principle, which is one of the best practice when it comes to DevOps kind of scenario. You don't want to give username, password. To create a dedicated service account, and this account can pull images from the container registry. This kind of feature is not currently supported with this approach. There is also the virtual network limitations where not all communication can happen very easily. If you want to have advanced scenarios, like you want to do peer-to-peer communication kind of setup, this is not supported. Init containers is again another feature of Docker or Kubernetes, which is not supported in the virtual node. And daemon sets. Again, this is a daemon set is kind of limitation in most of the cases. So what we saw so far was mainly scaling based on your demand, which is more of compute related. But not all workloads are really compute related. You might have architecture where you are writing event-driven solutions, and not always you will have CPU or RAM being impacted by events. And in such cases, you might want to have a different approach where you're trying to scale based on the number of users. So the benefit of this is you're not depending just on RAM or CPU, but you're looking at a different approach. Your matrix or your criteria for scaling is events in this case. And this solution can work with other options like it is not purely with events. You also have virtual node where you can combine event-driven scaling with virtual node solution. So it's sort of extendable. Cons, because I'll be talking about KEDA as a framework, this one is in preview right now and it's not production ready yet. So you'll have to wait for some time. You can try it in your development environment, but not for production ready support at the moment. So let's start with KEDA. What is KEDA? KEDA stands for Kubernetes-based event-driven autoscaling, and this is how the architecture of KEDA looks like. So you have the typical Kubernetes store at the center. You still have the kubectl CLI. You have KEDA, which acts as a matrix server and the adapter, and then it creates behind the scene a horizontal pod autoscaler. And this is based on something like an external trigger. So for example, you have, let's say, Kafka, or you have RabbitMQ as one of your event stores. You can scale the number of pods based on the number of events that you have in your RabbitMQ queue or your Kafka topic. Let's say you have HTTP trigger. Then based on the number of HTTP requests which are pending for processing, you can create additional pods to address those. If, let's say, those requests are not getting addressed faster. And because this has the matrix or the information available in the server, the KEDA manages this horizontal pod autoscaling. So it can go from 1 to n, or it can also scale down from n to 0, or the number of new instances that you specify. So let's look at what are the prerequisites for KEDA. First one is obviously a Kubernetes cluster has to be there. Then you need Helm. So Helm is like a package manager for Kubernetes. So if you have used, let's say, NPM or NuGet, if you're a .NET developer, or Yum, if you are on Linux. So Helm is like a similar package manager specifically for Kubernetes. And finally, you use a Helm, what is called as a package to install it using KEDA. So there is already a package created by KEDA guys, and you can install that using Helm. In terms of different sources that KEDA supports, specifically with Azure, it supports the Azure Event Hub, Azure Service Bus queues and topics, and Azure Storage queues. In terms of the messaging platform, it supports Kafka, Prometheus, RabbitMQ, and Redis List. And in terms of AWS, it supports CloudWatch and AWS Simple Queue Service. These are just basic ones, and there are more and more scalars and resources being added. There is also support for Azure Functions. It integrates quite nicely with Azure Functions, which is again a serverless offering from Microsoft. So let's have a quick look at one of the demos that I've created. I have a reference application which I created last year as one like a learning series in Singapore Azure User Group. This is available. The recording of this are also available. It was like a 6-part series. So if you go to that link, GitHub link, you will find all the 6 parts. So this covers, right from the beginning, how you containerize an application, how you put it on Minikube, how you scale it to Kubernetes, and how you can also do CI/CD. So this is a very simple, like a tech talks management application which has 3 components to it. The front end is ASP.NET Core MVC. Middle layer is .NET Core Web API, and on the database side, I'm using SQL Server 2017. So I use parts of this application for this demo. I've used the middle part, API, and instead of SQL Server, I'm putting those messages onto a RabbitMQ. So my setup is slightly different for this demo purpose. So the producer would be .NET Core Web API. I'm not using any UI, just to keep the demo very, very simple. I will simulate the load in other ways. Kubernetes version is anything greater than 1.11 would do. I'm using, I think, let me see, 1.12. We'll see during the demo. And when it comes to the web API, it would produce 1,000 messages onto a RabbitMQ topic. The consumer is a .NET Core exe, and it tries to read 10 messages in a batch. And it tries to simulate like there is a long-running process by having 2 seconds sleep between every message that it processes. And the messaging component here is rectangle. So let's have a look at this demo. So this is the cluster which I have provisioned already. And as you can see, it's 1.12.8 version. And if I go to the management UI of Kubernetes, I can see the number of nodes. Connection got lost. So you can see that it has got 3 nodes on that particular cluster, and we can also look at one of the nodes to see what is running on that. So on node 1, you can see it's using only about 5% of the resources, and there are only 4 pods allocated at the moment. I can also do this same thing like what Sebastian was doing. I can use the kubectl API and I can say describe node or describe pod, and I would get a similar information on the command line as well. Okay. Now let me show you quickly the code, how it's organized. So I have some PowerShell scripts here which I use mainly for ease. So this is the browse script which is connecting to the cluster from my command line. I give the resource group name and the cluster name, and that's how I can see that UI, the management plane of Kubernetes. When I create the cluster, so before this demo, because it takes about 15-20 minutes, I have another script which is quite handy in terms of what I want to create. So these are the parameters it takes in terms of what subscription I want to use, what is the resource group name, which location, what should be the cluster name, what should be the number of total nodes, and the version of Kubernetes. And then it goes and runs this AZ commands or Azure CLI commands. And it's creating the cluster here in the first step. Then it gets the credential where I'm able to connect from my local machine to the cluster. That's where you need to get the context from the Kubernetes cluster and store it on your laptop. That's how my command line from my laptop can communicate with the cluster in Azure, Kubernetes cluster. I'm also having role-based access here, so I need to enable the role-based access. And as part of KEDA install, this is where I'm setting up the repository for KEDA. So I apply the update of KEDA from GitHub repository KEDA code, and to install KEDA I use helm install, and these are the parameters which I pass. So with this my cluster is all set up. I can look at the objects that KEDA has created when I use this deployment. Network is very slow. Okay, so you can see the first one is a pod, then there is a service, and then there is deployment and a replica set. We can also see these objects if I go to the UI. So if I go back to cluster, and if I filter by the namespace of KEDA, I should be able to see those same objects. So that's the namespace. Yeah. So the same information that we saw on the command line is also available here in the UI. Now let's have a quick look at the producer and the consumer code. So the starting point here is there is an API called TechTalks API which accepts the request for creation of TechTalks, and this is where I am creating those 1,000 messages. So if you look at this code here, create, it creates some sort of dummy TechTalks. I'm using a library called Faker. So if you are using like unit testing, you can use this library to generate like fake data sets. And this basically takes sort of rules for all the objects or all the properties that I want to set. I can say for ID, for example, generate a random number between 1 to 1,000. For the TechTalk name, use the Lorem Ipsum word, randomly pick one word. For category, give a random number between 1 and 5. And based on these rules, in the end, I can say generate. And I can give the number of objects that I have to create. And all these objects are then passed to producer, RabbitMQ producer, which is sending them on to the RabbitMQ. So this one is event publisher, and if you look at the definition of send messages, it takes that list of TechTalks, it creates a connection to RabbitMQ with the host name as RabbitMQ, user and password. This is for demo purpose, so that's why I have hard-coded user and password. Don't do this in production. Then we started creating a connection object, and we define a queue, which is based on a queue name, a durable queue. So if something goes wrong and your the container which is storing RabbitMQ gets killed, the messages will still be persisted and they are durable, and they will continue from where they were processed when the container comes up. And then I serialize these talks and just add them to the message queue. So I'm doing a basic publish, and these messages are published onto the queue. Once we have these messages, the other side is consumption part. So let's look at the consumer. So here it does the reverse. It connects to the same RabbitMQ queue and looks at the similar properties like queue name, durable, less. There is one basic quality of service which I am setting here. So I am setting the number of messages that I want to fetch in a batch. So I am specifying the batch size as prefetch count as 10 here, because I don't want to fetch all the messages at once. And then I deserialize that message which comes up, and just to simulate like a heavy workload, I'm sleeping for 2 seconds, and then acknowledging after 2 seconds that I have processed the message. And then just log which message got processed. So let's generate this workload and see what happens. So I'm using Postman here, and I'm hitting that TechTalks API, the producer. Looks like it was successful, the request was sent. Okay, can you see what's happening here? RabbitMQ consumer. So it's increasing from 4, then 8, from 8 to 16, and at some point it should stop at 30. Okay, while this is scaling, let's also look at the RabbitMQ management UI.
Change the point.
So here I am doing a port forwarding. Port forwarding is again a concept with Kubernetes where you map a remote port to a local port, and then you can connect to that particular service as if it was running locally on the machine. So I am port forwarding to 15672 port, which is the RabbitMQ management UI port on the Kubernetes cluster. So as you can see here, it is kind of stabilized as at 30. So I'll show you why it's stabilized at 30. Let me first get this working. Show me the queue here. For some reason it's not showing. So what I was hoping to show you was this. In the management UI, you can see each of the consumer, and you can also see what is the prefetch count of the messages. And if we go slightly up, it also shows the how many consumers are running here. So it will show the spike, how many messages got pumped in, this bit here, how many are ready, that means how many are currently being processed, and you can also see how many consumers and the flow. So after a while you will see them dropping down because you get the acknowledgement that the message has been processed. I wish I could show this slide so that you believe what I'm saying. It looks like there is some problem with the network. Not able to even load that template.
They trust me for sure.
Thank you. Okay, so Sebastian, he made a good point while doing his demo that AWS, for example, they don't log into the system, they don't debug for you, but we all are developers, right? At some point, we need to debug into the system. And if you want to see what's happening with the bots, you can use this approach here. To see if you're writing, let's say, a log message, it would be visible in the output section. So, for example, this is also lost. You'll have to bear with me for about a minute. This was like seconds during the dry run. I tested it backstage. Not able to get, but luckily I have one of the logs open. So this one is for the consumer, one of the consumer. So you can see here, this is what I'm printing as part of that details of the message. So one of the message got processed at 42 minutes 28 seconds, and because of the 2-second delay, the next one would be at 30. And like this, it would keep processing one message every 2 seconds. So this is how you can see the logs. So this you can hit here, logs, and you will be able to see. If I was able to connect, you would have seen that. So how did it reach that 30? Let's look at that definition. We managed to scale from almost 0, or started with 4 and it reached 30 pods. So this is the main object, the scaled object which is provided by KEDA, which does that. So I'm saying in this case, give me a metadata. The name of this is RabbitMQ consumer, and this is the spec for that. So I say look at the requirement name, RabbitMQ. These are some of the optional properties which I can specify, saying polling interval every 5 seconds, cooldown period 30 seconds. I will come to cooldown period a little later. Minimum number of replicas and maximum number of replicas. So it will scale from 1 to 30. Once it reaches 30, it will not add more replicas of this particular deployment. And the trigger for this is of type RabbitMQ. I'm giving the queue name. There is the host or the connection URL, and there is also queue length, which is 5. What this means is, look at this queue on RabbitMQ at this particular connection. If there are 5 messages in the queue, you scale. So it will keep scaling until it reaches 30. Then when there are less than 5 messages, it will start scaling down. It will scale to the minimum of 1. So at 1 it will stop. It will not make it 0. Default is 0. So if you don't specify minimum, it will kill all those dynamically created pods. And cooldown period is 30, which means it will wait for 30 seconds before destroying that particular container, just to see if there are more messages coming in. So let's go back to the presentation. So this is the scale object that I just now explained to you guys. So that brings me to the end of my demo and the talk. Here are some references. So these slides are already available on 2 sites which I used mainly for speaker deck and SlideShare. So I've already published them. I'll share the link at the end, so you can find these references there. If you are interested in learning more about Kubernetes, there is a really handful resource or useful resource which I found. This is from Microsoft, what they call 50 days from 0 to hero with Kubernetes. This is done by the co-creator of Kubernetes, Randall Burns, and he takes you through like a 50-day journey of learning Kubernetes, right from very basic to advanced concepts. This has got links to some videos, and there are some references to books, and those videos are quite short, like 5 minutes or 10 minutes, not more than anything 10 minutes long. So you can have a look at this. This is quite useful. If you want to learn about containers, you can refer to these books. These are available on GitHub. And that's all from my side. So these are the links I mentioned. Any questions? I have some time to take questions, I guess.
Yun kasi Mike, tumayo ka.
Right. So is it so in the demo is the broker containerized?
Yes, everything is containerized.
So is it possible to have the broker not containerized? Like
yes, that's possible.
Right.
Broker not containerized is okay because you are looking at the message as a source. You are not looking where the message is coming from. What is getting scaled is your consumer. So consumer is a .NET exe and that is containerized. So that runs as an individual pod and that is what gets scaled across. So it's not scaling the broker. Broker remains the same. Yes.
Sorry, yeah, right. So does the broker have to be on Azure or is KEDA like open source? You can use it anywhere.
You can use it anywhere. KEDA is actually a joint project between Microsoft and Red Hat. So broker again, it's just a source, right? In this case, I'm using RabbitMQ. RabbitMQ could be anywhere. As long as your AKS cluster or your Kubernetes cluster can connect to that broker, it can communicate with it, it should be fine.
Awesome. Okay, that's it. Thank you.
Thank you. Any other question? Okay, so it's running. So you can see here, this is how we can see the logs from the container. So this is from consumer. You can also go to the producer and see the producer logs. So here I'm just publishing this from the producer side. So if I go back to the code, you can see this message. This is the one which is getting inside that container. And if everything is fine, it should scale down now. So you can see it's come back to one message, one container. The RabbitMQ consumer, let me just bring it back up. Here, it is come back from 30 to 1. So it has finished processing those 1000 messages, and that's where it realizes there are no more